Hi there, thanks for joining us. This is Space Nuts, the astronomy and space science podcast. My name is Andrew Dunkley, your host. Coming up, we will be talking about lots and lots of things because this is an all-audience questions episode. So this is where we throw it over to you and you throw a lot of stuff at Fred and see if it sticks. We'll be talking about fast blue transients, the cooling universe and gravitons, amongst other things. Ghost galaxies, the heaviest isotopes in planet formation, and so much more coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And to answer all of your questions with precision and perfection is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you doing?
I'm feeling a lot better than you.
Yeah. It's like an exam, you know. It's kind of like going into an exam that you haven't studied for.
I did that a lot.
Yeah.
I did that a lot.
I did too. Second science mathematics at the University of St Andrews nearly got me. In the end, I passed it by the skin of my teeth.
Yeah, well, I wasn't so lucky in a lot of my exams, but, I did it to myself. I look back at my younger self and say, you buffhead. But,
oh, yes, that's absolutely right.
Yeah. Don't you wish you could have a time mirror where you could just go and sort of tap on it? Your younger self appears and you go, listen, this is what you need to do.
For goodness sake. Exactly. Yeah. I'm thinking of writing a book about that, actually.
I was going to say, that'd make a great science fiction novel, but it's probably already been done.
Yeah.
All right, we better get into it. Now, we've got some audio questions. We've got some text questions. These are all pretty well brand newies. And we will start with a question from Derek.
Hello, Andrew and Professor Watson. My name is Derek from Kitchener, Ontario in Canada. I'm a long-time listener and first-time questioner. I have a question regarding the cause of fast blue optical transient explosions, particularly the one called AT-2018 Cow, nicknamed the Cow, discussed in a previous episode. This solar system-sized explosion was considered odd due to it being extremely flattened out like a pancake rather than a typical sphere. Could this flattened shape be caused by extremely rapid spins, say by a neutron star, or perhaps two objects spinning up until they're torn to pieces? Thanks for the great podcast and books. I'm currently halfway through Star Craving Mad. There.
There's the person who bought it.
Yes, I wondered who it was. The best thing about that book is his title, which I didn't think of. It was Marnie who thought of that. Star Craving Mad. Tales from a Travelling Astronomer. That's what it's
indeed.
Thank you, Derek.
Lovely to hear from Canada as well. Thanks for sending your question in, Derek. Fast blue transients. Yeah, we did talk about that recently, and this disc-shaped explosion that has defied logic. Or has he got the answer?
Well, actually, I think he has. I was just going to say the answer to Derek's question is yes. I think both the things that he highlights, the possibility of it being a rapid spinner, or being something that's disintegrating. Both of those could be correct. I've got to remind myself actually of the details of that. I know we did talk about it, but to be honest, these things come and go so quickly that I've only got half a gig left of memory in my head. That's not really enough for all these facts. It's an object that is probably about 200 million light years away because it sits in a galaxy. It's at least spatially coincident with that galaxy, CG 137068. And it is in a sense, it's the most local of these. I should say they're called F-bots, by the way. Okay. I think we talked about that at the time. Fast blue optical transients. In fact, it's being hailed to some extent in the literature as the sort of prototype of its class. except that it is a bit unusual, and it's an object that has a lot of mystery attached to it. It's clearly an explosion. The transient itself is an explosion that was. I think it was this the one that was known as the brightest of all time boat. I can't remember whether this one was given that title, but it's certainly up there with the boats. And it's basically, the estimates are 10 to 100 times brighter than a normal supernova. It's been, it's kind of one of these objects that they're characterized by something called a Fred. I thought I'd just drag this in. Do you know what a Fred is?
I do not.
It stands for, it's in physics really, fast rise exponential decay. Fast rise exponential decay. And it's any signal that goes up very quickly and then, decays very slowly. And in a way that covers all supernovae and, the objects in that sort of class. I was just looking online for a light curve for COW, SN 2018 COW, usually called the cow. Let's see if I can find one, because that would, here it is. That's good. I've got a bolometric light curve, and it is exactly that. It's a Fred. It goes up very quickly and basically decays very slowly. Bolometric is a measurement taken across all wavelengths. I don't know whether you knew that, Andrew. It's measured with a thing called a bolometer, which looks, it's a broadband detector. Most of our detectors are limited to a specific wavebands, but a bolometer isn't. It's usually used actually in the microwave region of the spectrum. But it also, of course, because it's a fast blue optical transient, it's got optical emission as well. And I'm just looking now at the way its spectra decayed. It's basically what's called a hot black body emission, which that's the shape of the spectrum. So I think with F-bots generally, and with this object in particular, I think really there's not that much. There's not that much hard and fast astrophysics that means that there is a common view of what they are. Quoting, for example, from our well-known source Wikipedia, the precise definition of what constitutes a fast blue optical transient is currently contentious in the literature, largely defined by the observational properties rather than the underlying mechanisms or objects. And that's because we don't really know what they are. And that particular article goes on to make the point that even when you lump them all together, when you look at the details of the growing number of these events, there's such big variations in their properties, even though they're all classified as fast blue optical transients. They've got different properties, different spectra, different light curves. That's the up and down bit, the amount of radiation it receives. So it's saying, well, it says it's potentially indicative of different progenitor channels or explosion mechanisms. In other words, all bets are off, and I think Derek's contribution is as good as anybody's.
Okay, so he might be onto something.
Yep.
Okay.
That's a good suggestion.
Indeed. All right, thank you, Derek. Let's move on to a question from Renny, who is a regular sender-innerer. Renny says, what's your thinking about galaxies like Glass Z or Glass Z13 and how they developed to such a mature state in the early aftermath of the Big Bang? Could it be they wormholed their way into our universe from one that was separated by a membrane we can't understand, when possibly the fabric of that membrane was disturbed by our universe's beginning? That's come from Renny. What do you reckon?
So it's a Lyman break galaxy. That means its spectrum tells us that it's at a high redshift because the ultraviolet features in its spectrum are moved into the infrared. And I think so. The Z13 or Z13, I guess, refers to it. Oh, wait a minute, that's 12. I don't know whether that's a numerical. Yeah, I think 13 is its redshift. Z. So the redshift, of course, is a measurement of how redshifted the spectrum is. And when you get up to 13, you're looking back to the very early phase of the universe. Just give me a minute. So yes, all right, GLASS. I did that. Now that's an acronym I haven't come across before, which is the Grism Lens Amplified Survey from Space, one of the instruments using the James Webb Telescope. A GRISM, by the way, Andrew, I used to use these when I was a kind of practicing astronomer, is a combination of a grating and a prism, which is why it's called a GRISM. Both of those have the effect of splitting light into its rainbow spectrum colors. And a prism we're all familiar with. A grating we're perhaps less familiar with, but it consists of a lot of lines ruled on a substrate, usually a bit of glass, which has the same effect of dispersing light. The phenomenon was discovered by a Scotsman by the name of James Gregory. In the late 1600s, he held up and he actually was the professor of astronomy in the university that I went to, and I was there shortly after him in the 17th century. He discovered it by holding a seagull feather up to the sun and noticing that it split light up into a rainbow of colours. That's an aside on the technology, which is my strength, whereas high redshift galaxies are something that I stand on the coattails of my colleagues. So it's redshift. Hang on a minute. It's yes, okay. So that's why there's some confusion here. It used to be called GLASS Z13. It's now called GLASS Z12 because its redshift has been reevaluated. Right. A redshift of 12 still means it's one of the earliest galaxies ever observed. Dates back to maybe 350 million years after the Big Bang. So we're talking about a very, very early galaxy. Now, having established all that, would you mind reading Rennie's question again?
Not at all. What is your thinking about galaxies like GLASS Z13 or 12? And how they developed to such a mature state in the early aftermath of the Big Bang. Could it be they wormholed their way into the universe from one that was separated by a membrane we can't understand, when possibly the fabric of that membrane was disturbed by our universe's beginning? So he's asking if we snatched this universe.
Yeah, I get that, and that's a very nice idea. We don't. There's a lot of study going on. It's it's kind of become again a hot topic. Have the idea of wormholes. We've got no evidence of the existence of wormholes, but they're still mathematically allowed. And there's been a lot of recent research, and in the fairly mainstream, physics realm, looking at how and why they might work, and whether we are missing something by kind of ignoring wormholes. I find that hard to believe that it could happen. I think what we're seeing is the evolution of properties of galaxies. Exactly. Renny's absolutely right. This particular galaxy has surprised everybody because it's only 350 million years after the Big Bang. And everybody thinks that the things that we see in the galaxy, the elements, that it really should be older than that. In other words, have we got the date of the Big Bang wrong? Now, that is unlikely because our observations of, the physics that tell us the date of the Big Bang are pretty rock solid. And we talked about it already last time when we talked about Arno Penzias, the person who discovered the cosmic microwave background radiation with his colleague Bob Wilson. That discovery really set the seal on our understanding of the age of the universe. You combine that with the Hubble flow, the fact that galaxies are moving away from us, which is what really started the idea that there was a Big Bang. But you combine those two together and you get measurements which, yes, there's slight discrepancies. There's something called the cosmological tension at the moment because there's two slightly different values for what's called the Hubble constant. Yeah. But nevertheless, the age of the universe is pretty solidly back at about 13.8 billion years. So I think the issue here is not a cosmological one. It's not that we've got our picture of the universe wrong. It's that we've got galaxy evolution wrong. That we are not really understanding fully how you can produce the characteristics that we see in an early galaxy like that in such a short time. Mm-hmm. So it's an interesting conundrum, but I think it's one that's completely resolvable. I don't find it one that needs esoteric explanations like things popping out through wormholes on the fabric or the membrane fabric of the universe, and that's what it might be if that's M theory that says that the universe might be, or brain theory, it's sometimes called BRANE, that the universe might be just sitting on one of many membranes, each of which holds a universe. Lovely theory. You get a Big Bang, by the way, when membranes bang together, Andrew.
Yes, I can imagine.
Yeah.
Well, I'm sure a lot of people still speculate over that possibility, but it's probably something else we're missing in galaxy development early on. But thank you, Renny. Let's go to an audio question from Dave.
Hey guys, it's Dave from Calgary, Alberta here. I'm British, but I live in Canada, hence the accent. But I have a question about the expansion of the universe. I'm 99.9% sure I'm wrong about my theory, but I've never found an answer to explain why I'm wrong, and I'm hoping you guys can help me out. So obviously the universe is expanding and it's speeding up. My question is why won't it ever slow down? And I've heard that the dark energy is making it speed up. But my theory was similar to how a gun, a round out of a gun, speeds up before it gets to a certain point and then starts to slow down. Could that happen with the universe, or what's the reason why that won't happen with the universe? I'm guessing it's to do with dark energy, but I'd love to know your answer to it and probably explain it to me perfectly. Thank you very much.
Thank you, Dave. Couple from Canada today, which is nice.
That's great.
It's probably a long bow to draw to compare the firing of a bullet with the expansion of the universe, because the bullet's affected by the curvature of the Earth and gravity and atmospheric conditions, which all add up to stop the bullet eventually. That doesn't exist in space, does it?
No. Dave's question is a good one, and actually I'm going to be in Canada in about 2 months, so it's nice to have two Canadian questions. The bottom line is Dave's right to question this, because we can't guarantee what the universe is going to do. We don't have any sort of control over that. All we can do is observe what it's doing now, and through the magic of the fact that we can look back in time, we get a good idea of what it's done in the past. So I think an analog of the kind that Dave is thinking of would be better served for the expansion of the universe, not by a bullet, but by a rocket. Because this is the thing that we think is happening. And we talked about this a couple of weeks ago with the cosmological constant and the equation of state and all that stuff there. The idea of dark energy is that space itself has what might be called a vacuum energy. It's just got an energy of its own. And the energy is in some way proportional to the volume of the space. That's what seems to be happening, even though the numbers, as we heard a couple of weeks ago, don't actually tie up exactly. But it seems to be that as space gets bigger, the energy of space gets bigger too, because this vacuum energy, that this sort of repulsive force that's pushing space apart, is proportional to the space volume itself. And so what you've got is something that is unlike a gun, which is propelled down the barrel and then doesn't have any propulsive force keeping it going, and that's why it slows down. And its air resistance, I guess, is the main contributor to that. But all the other things that you mentioned, Andrew, curvature of the Earth and gravity, they all play a part too. But if you think of a rocket, what you've got is basically a motor that is actually running for a long period, and it's providing that energy. But also with a rocket, certainly one that's leaving the surface of the Earth, what you've got too is that as the thrust of the rocket, which is constant because it's determined by the chemistry of what's going on in the combustion chamber, the thrust is constant, but the acceleration increases because the mass is going down. As the rocket goes along, you're burning up fuel, so it's lighter, and so it gets more of an acceleration. And so that's really a better analog, I think, for what's going on with the accelerated expansion of the universe. But as I've said, we don't know. We simply don't know what the universe is going to do. We thought until the 1990s that it was definitely going to slow down because of all the material in it, that would have a gravitational influence that would tend to break the universe, and that its acceleration would be its expansion would be slowing down. But that is not the case.
Okay. So watch this space, Dave, because, it might sort itself out in a couple of weeks.
Well, if it does, that's good, because we can talk about it on Space Nut.
Yes.
Oh, no, by the way, the universe in 10 billion years' time is going to stop.
Yes. Let's get off. All right. Thank you, Dave. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Okay, let's take a short break from the show to tell you about our sponsor, NordVPN. Now, I've told you about virtual private networks many times in the past and how valuable they are if you are using a device in a public arena like an airport or a railway station or a library or maybe a hotel or something like that. Anywhere where there's a public Wi-Fi system, a VPN is a very good idea because it protects you. It gives like a firewall between you and anyone who might be trying to hack your device and get into your personal information or your bank accounts, whatever it is that motivates them. And these days is so very easy to get hacked. I mean, it's happened to a lot of people, and sometimes it costs them tens of thousands of dollars. But our sponsor, NordVPN, can help. Now, we have a special URL which you can log on to and get a unique deal as a Space Nuts listener. All you have to do is put in a search for nordvpn.com/spacenuts. Click on that, and it'll bring up a page that will indeed give you a really great offer. It's a New Year's deal, in fact, a big discount plus 4 extra months of NordVPN with their ironclad 30-day money-back guarantee. So that's what you met with on the page. It explains all the things that NordVPN can do for you, safety in browsing, secure your passwords with NordPass. Now, that's my favorite tool. I have so many passwords and usernames, I just can't keep up. But I can store them all on a fully encrypted system that is basically secured by a single password. It's the only one you have to remember. And the links that you set up within this system enable you to just jump to whatever page you need to on any device without even having to think about it. Brilliant. Highly recommend NordPass. But there are so many other features as well. There's Nord Locker, which is basically cloud storage and very secure indeed, and so many other things. So please remember, 30-day money-back guarantee. Just click on Get the Deal at nordvpn.com/spacenuts and see what's right for you. You can get the whole bang lot, or you can just select a smaller option. Regardless of what you do, you get the extra 4 months. But the longer period you invest in this for your own security, and the more options you take up, the lower the price over the longer term. It's a great deal and very well worth investigating. That's nordvpn.com/spacenuts. I use it all the time. nordvpn.com/spacenuts. Check it out. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Okay, Fred, we'll go to another question from the Netherlands. After the Big Bang, the universe started to cool. How long after the Big Bang was the universe at room temperature? And how long was the universe at room temperature? And can we set a telescope to zoom in on that moment? Thanks for the answer. Kind regards, Joost from the Netherlands.
Yeah.
Room temperature. Does he mean actual room temperature, or the universe's interpretation of room temperature?
No, I think he means room temperature.
Okay.
Let me just see if I can answer this precisely.
All right.
I can give a hand waving answer, and certainly we can't tune a telescope to look back on it, and I'll tell you why in a minute. But let me just see if I can bring up a cooling curve for the universe that would actually give us a time when the temperature was room temperature. Here we go. I've got loads and loads of cooling curves. And there's an odd one. So it may well be that it's longer than I thought, that the universe is actually older. I was going to say it was probably within the first few minutes. And of course, you can't see to within the first few minutes of the universe, because we can't see anything when the universe was less than 380,000 years old, because that's the age of the universe at the level of the cosmic microwave background radiation, beyond which we can't see. So we've got this veil that's drawn over a universe younger than 380,000 years. Mm-hmm. It is in the region of 1 million years, by the looks of it. 1 million years. It's before the formation of galaxies, and you're still you're not quite still in a radiation-dominated universe, but you are close to that. I think it's longer than I thought it was, and it looks as though it's of order of the same length of time as the time it took for the universe to become transparent, because that's the time that we're looking back to in the cosmic microwave background radiation. You're looking completely baffled, Andrew, and I'm rambling here because
well, I've found a conflicting article that says that during a very brief window between 10 to 17 million years after the Big Bang, the temperature of the cosmic microwave background was about 80 degrees Fahrenheit, close to room temperature.
Okay.
That was from R.B. Loeb.
Oh, yeah, well, yeah, he's a name to reckon with. He's a very controversial figure. Just tell me what the number was. No, tell me what the number was there that you said. Read that bit again, please.
During a very brief time window between 10 to 17 million years after the Big Bang, the temperature of the CMB was around 80 degrees Fahrenheit.
10 to 17 million years.
Yes.
That's not a brief interval. That's 7 million years.
It is. And I did find another article that said 6 million. So there's a lot of speculation.
Well, so I'm saying in the region of 1 million. He's saying in the region of 10 million. In cosmology, that's the same thing.
Yeah.
So That's interesting. No, it's a really interesting question, though. I didn't get the questioner's name, Andrew. I don't.
That was Joost.
Oh, Joost, that's
from the Netherlands.
Yeah. It's a really
put this in
question.
the homework folder if you like.
Yeah, we should try and tie it down a bit more. But Avi's probably right. He I think he's still the director of the Howard Smithson IFA, the Institute for Astronomy, one of the most renowned astronomical entities in the universe. Sorry, in the world, possibly the universe as well. But always looking for evidence of extraterrestrial intelligence. He's the gentleman who thinks Oumuamua was a bit of a spacecraft that flew through the solar system.
Yes, indeed. All right. Well, we'll follow that one up for you, Joost, but there are some people who speculate or believe it was probably 10 to 17 million years after the Big Bang and lasted quite a long time. Thanks for your question. Let's go to Brian. Oh, look, it's a black hole question.
This is Brian Pulowski from Columbus, Georgia. My stepson and I were talking about black holes, and he asked me a question. He's 10 years old, by the way. Can a black hole be destroyed? What do y'all think? By the way, we love your podcast. We listen to it on the way to school every morning.
Very cool.
Fantastic. Yeah,
thanks, Brian. Yep. Can a black hole be destroyed? Yeah, I don't know. That's a good question. I would suspect yes, but it'd have to be very extreme circumstances.
So yes. So the sort of standard answer to this is yes, but under very unextreme circumstances. So we know from Stephen Hawking's work in the 1970s that's been verified by analogues rather than by observation. But we know that black holes can evaporate they release what's called Hawking radiation, which is electromagnetic radiation. It's very, very weak radiation, however, and takes a very long time for the black hole to evaporate altogether. In fact, longer than the current age of the universe for pretty well all black holes. There may have been some tiny, tiny, tiny ones that evaporated early on in the universe, but the evaporation rate is so slow that the time is very long. So that's the answer. The answer is yes. They can be destroyed because they don't last forever. They last nearly forever. Numbers like 60 billion years are, the ones that I've come across. I think I wrote about that in one of the books about how long it would take an Earth-sized black hole to evaporate, and it's a huge, huge number. But whether conditions in the early universe, when things were so extreme, whether if you could throw a black hole into that early universe, it would survive. That's a different question. I suspect. I mean, some of the thinking is that those extreme conditions in the early universe came from a black hole anyway. Roger Penrose's idea that this formation of black holes in space, giant black holes, are big bangs, so that tends to shed a bit of light on that. But I think for Brian and his grandson, I think the answer is yes, they can, but it's a slow process.
Okay, there you go. Let's go to our next question. Thanks, Brian. And regards to was it grandson or nephew? I can't remember.
I'm sorry, I probably got it wrong there.
That's perfectly okay.
Your relative
we just made Brian a lot older than he probably is.
Sorry, Brian.
But, when you're talking about the age of the universe, it's not much of a difference.
Yeah.
Mark has sent us a question. With regard to the recent mention of the ghost galaxy, such as Aztec 71, if it turns out that there are many far infrared visible galaxies in the universe, would the presence of all their normal matter significantly reduce the need for the existence of so much dark matter? Thanks for the wonderful podcast, Mark. He's from Bloomington, Indiana. Ghost galaxies and infrared galaxies, presence of normal matter significantly reduce the need for the existence of dark matter, so much dark matter.
Yes, that's right. I think I'm just remembering our chat about that, that it's a galaxy that in normal telescopes is invisible because it's such a dusty galaxy. And I guess the idea is that this has been, was it observed by the James Webb Telescope? That's right. That's the story that we did back in December. So I think the physics of this particular galaxy, Aztec 71, are fairly clear cut in that it is real matter that is obscuring it. It's dust. It's the normal smoke-like material that we know permeates galaxies. In our galaxy, you could see it. Certainly, there's the dust lanes in the Milky Way. Those dark clouds in the Milky Way are just the same sort of dust that we're talking about here. But it's normal matter that is contributing to its invisibility. So there is certainly an interaction, though, with dark matter, because galaxies tend to be rich in dark matter, and I suspect that any dark matter confusion that there is because of the fact that we can only see this galaxy in the infrared, I suspect that is. I think it's a minor detail compared with our general understanding of dark matter, which actually comes not just from looking at individual galaxies, but from the structure of the universe. We can actually probe the geometry of the universe, which leads us to information that's about the amount of dark matter that there is in the universe, and that's consistent with what we see in individual galaxies. So I don't think there's an issue there, but it's a nice thought.
Yeah. Good on you, Mark. Thank you so much. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Okay, Fred, we've just got a few more questions to go before we wrap this one up. And we didn't get the name of this listener because it cracked up at the beginning. So apologies, but we got the general gist.
Nicholas here from Perth again. I was listening to your episode on the oldest black holes, these supermassive black holes that occurred from earlier in the start of the universe. And I was just thinking that if gravitons existed, could they have been an elementary particle formed in the black hole in the Big Bang? And could they have clumped together to form the first black holes? Thank you. Bye.
Thanks for the question. So did you get the guts of that?
Good. Yeah.
Good. Because I was trying to remember what he said.
So if gravitons existed, could they clump together to form black holes? And I think the answer is no, because gravitons, if they exist, would be bosons, which are force carriers, and not, is it leptons, the other kind that make up matter? And you need matter to make black holes. So I think that is the answer. Actually, I should check that. I'm not talking rubbish there about that.
Well, gravitons are theoretical, aren't they?
Yes, they are. Yeah. Actually, leptons is the wrong word for what I'm trying to say. But basically, bosons are force carriers, and the other kind aren't. And you need the other kind. To form black holes. I'm sorry, I throw in the leptons, which are actually a different sort of it's a different category of elementary particles. But you get the idea that they're the wrong kind of leaves, if I can put it that way.
Yeah, okay.
As British Railways used to say when their trains were late, wrong kind of leaves on the track. So the gravitons, I don't think, could clump together to make a black hole. I'm not
All right.
I'm not a particle physicist, but that's the way it would look to me.
Fair enough. All right. Thanks for the question.
Yeah, great question.
Yeah, we're getting a lot of pretty heavy-duty ones today. This one comes from Garrett I love where Garrett lives, Dripping Springs in Texas.
Yeah.
That sounds like a fun place.
Yeah, I'm going there. I'm actually going there. Yeah.
No.
Next month. Yep. The month after next, because that's near where the eclipse path is. So we're going to be in Dripping Springs, passing through. It's very beautiful. Yeah,
I'm sure it is. He says, during the differentiation phase, as proto-Earth accreted out of the collapsing disk of dust, while a lava glob formed, the elemental species were able to rise and fall to an equilibrium depth within the Gluck ball. This is all official speech here. Each according to its atomic weight. With the heaviest isotopes also being the least stable, I might have expected everything fissile, like U-235, to sink to the centre of the core with the weight of the entire mass of the planet pressing on all sides, till boom. Clearly, this did not happen. Why?
How do you know it didn't happen? Sorry, I didn't get the name there. Was that
Garrett? Garrett.
Yeah, that's right. Yeah, sorry, Garrett. There certainly is nuclear fission taking place underneath the surface of the Earth as we speak. There are natural nuclear reactors, which are basically what Garrett's talking about. They're in the probably in the crust, actually, rather than the mantle. So they're quite near the top. And that might come from later bombardment of the Earth by protoplanets or planetesimals that delivered those high-density materials to the surface of what was by then the differentiated Earth. So reactions do take place, and they are constantly doing that. But I think the difference is we don't get the explosive chain reaction that Garrett's thinking of, something that blows up. And maybe there just isn't enough of the material to do that, or the energies are not high enough. I don't know the answer to the question. It's a good one, but nuclear fission does take place within the Earth. And we actually think that the core is reasonably active in this regard, and it's one reason why it's still warm. So it's more like, perhaps, should I say, it's more like a nuclear reactor in a power station than a nuclear reactor in a fission bomb, an atomic bomb.
Well, that's
so. Yeah, so that's the short answer. And knowing what the mix of these fissile materials is that would actually give rise to such a situation is the subtlety that I'm not across.
Okay.
But it's a great question, and clearly well, as far as we know, there wasn't a boom. But yes, but it's not. The question's with merit, because fission is taking place, and it is one reason why we think things like orphan planets are visible, and these are planets that seem to exist without any star. We can see them in the infrared region of the spectrum because they're warm. And that warmth is thought to come from within the fission processes, nuclear reactions deep within their cores, which is not nuclear fusion, which would turn it into a star, but nuclear fission, which makes it warm.
Interesting. I don't know how I'm drawing this connection, but Garrett, wasn't there an early steam engine named Garrett?
It's not early. It's was developed in the 20s, I think. It's an articulated steam locomotive.
Oh, that's the one. Yeah,
Garrett locomotives, and they were used here in Australia. They
trialled them between Sydney and Dubbo.
Oh, there you go. Did they?
Yeah, that's why I remember it. It came up in our archival news segment that I do on the radio every day. Yeah, the Garrett steam engine. There you go.
They were
Garrett.
Big locomotives.
Yeah. They were certainly big and powerful. Thanks, Garrett. Our final question comes from, guess who?
Hello, Space Nuts. Martin Vermin Gorvine here, writer extraordinaire in many genres. And today's question is, how many habitable planets could you get in a single solar system? Like, what might the maximum be? And bonus follow-up question, could you have more than one habitable planet orbiting not the parent star, but a gas giant? So could you get like two or more moons of the gas giant, of a gas giant orbiting the parent star? And one thing that I can set your minds at ease about, I will never be asking for advice on telescopes because I brought up the subject with my wife, and she told me about a friend of hers whose marriage started downhill and ended in divorce when her husband started buying all these amateur telescopes. Can't wait for your answer on the habitable planet thing. Bergen Gorvine, over and out.
Martin, thank you so much. Always good to hear from him. Very entertaining as usual. All right. So, yeah, how many habitable planets, and could you have more than one orbiting a star or a gas giant? Look, you could throw any number up and you might be right or wrong.
Yeah, there's physics which would determine, how many habitable planets you might have in the habitable zone of a star. And intuitively, I'm thinking, that it certainly could be more than one. We think, well, that's not as daft as it sounds, because you could, if you put a planet in the habitable zone around a star is not very wide. That's the thing. You get too close and it's too hot. Get too far away and it's too cold. And the Earth sits right in the sun's habitable zone,
and it really upsets bears.
Well, it would. That's right, especially if they come in threes. So that's why you need the Goldilocks zone. So the orbital dynamics of an object being joined by another object within the same zone of a star's habitable zone might mean that one just gets kicked out straight away because they interact gravitationally. But when you think about it, we do know that there are ways that objects can share orbits, and most notably, when you think of a planet like, let's say, Jupiter, even though Jupiter's not in the habitable zone, that's accompanied by two swarms of asteroids, 60 degrees ahead of it and 60 degrees behind it in its orbit, called the Trojan asteroids. And they basically are centered on the Lagrange points, the two L4 and L5 Lagrange points. So that means that you can have more than one object sharing the same orbit, as long as they're in particular geometrical relationships. So I think the answer is yes, you could. I don't know what the maximum number is, but I think you could have more than one object that might be maybe not quite planetary in size, but big enough to be within the habitable zone. If you could, if you could set up a base there or something like that.
I imagine that most stars, except for maybe the super volatile ones, would have some kind of Goldilocks zone. So within each, there could be habitable planets. So we're talking squillions.
Yes. Oh, yes, that's right. In terms of the habitable zone, that's right. There was another aspect of Martin's question which I didn't quite get, because he talked about moons going around red giants, and moons go around planets, not stars. So I wasn't quite sure what he was getting at there. Did you?
No, I didn't catch it, but I maybe he means moons that are orbiting planets
going around. Yeah, red giants.
Yeah, I mean, could you have a habitable planet and a habitable moon within the same vicinity, perhaps?
Maybe.
So I suppose any combination is possible, isn't it?
Well, that's the one thing that we're learning as we discover more and more exoplanets. You know, we used to think the solar system was the typical system of planets. If other planets existed, then we started discovering other planets, and none of them looked like the solar system. It's very well ordered compared with many of the ones that we're observing. Part of that might be a selection effect, though, Andrew, because it's easy to discover big planets and not so easy to discover small ones.
Yes, which are usually the habitable ones, or potentially habitable ones. I suppose you also have to, draw a line under what is defined as habitable.
Yeah.
Like habitable for humans, all right, well, that reduces the odds significantly, but habitable for something that's alive, could be many, but then you've got to define what alive is.
Yeah, well, that's right.
It's going.
No definition of life. Yes, we don't have a definition for life.
Good luck with your telescope, Martin. Thank you so much for sending in your question.
Yeah, it's an interesting one, is that? And I think he's right. It can lead to all kinds of... Because astronomy, and certainly when it comes to buying telescopes, it's totally addictive, and you just get what's called aperture fever. You've got to have a bigger one to show a bit more.
Yeah, absolutely. Thanks, Martin. Thanks to everyone who sent in questions. Really appreciate it. Please keep them coming. You can do that via our website, spacenutspodcast.com, spacenuts.io, and click on the AMA tab to send us a text or audio question, or click the send us your voice message on the right-hand side of the homepage and have a look around while you're there. And maybe, if you're one of the social media followers, subscribe on YouTube or any of our other platforms. The more subscribers, the better. But that wraps it up for another show. Fred, thank you so much.
It's a pleasure, Andrew, and I look forward to more settled stories in the next few weeks.
I don't know about you, but I love the potlucks potluck approach to it.
Yeah.
Yes, I know you don't.
No, it's not that I don't. It embarrasses me because it reveals my levels of ignorance about certain topics.
Oh, gosh. No, I don't think so. I think it's, the people are throwing curveballs all the time. You can't hit them all.
No. I would like to hit one once in a while.
All right. Thank you, Fred.
See you soon. Cheers.
Bye-bye. Fred Watson, astronomer at large, and thanks to Hugh in the studio. Let me just check and see. Nobody home. All right. And from me, Andrew Dunkley, thanks for joining us. Hope you can catch us on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.